but I think I should rename this to Graph Learning 101 because I've got some researcher coming to me who researches graph learning and asking some very in-depth questions. So today, Graph Learning 101. I hope everyone recognizes this. If you don't, I might be in the wrong room. Google search. Behind Google search, there is a huge network of information, web pages, everything that's condensed into graphs, represented by graph, and that's powering Google search. And today, we're not talking about Google. These are other applications that are using graphs and learning from graph. I'm just picking up some of the ones that you all will recognize, and we're not going to talk about them either. Let's take a closer look at graph. What does it look like? We have nodes in a graph, and we have edges. These are the two key components that forms a graph. Stick with me today. We're only looking at the simplest form of graph. We're not going into any complicated stuff. We have graph here. And in a graph, we have nodes, as I mentioned. That means that on the node level, we have node level tasks, node classification, for example. In a social network, a node can represent a person, and we can predict if John will support England in the World Cup. I think it's fairly easy to predict if he's English. Then a node can represent a web page. In 1998, PageRank revolutionized search engine by learning from graphs and rank page importance based on the structures and connections between all these web pages. And then if a node is a picture, we have an application from Pinterest. They develop Pinsage, which constructs graphs based on users' pins and recommends similar photos to users based on their pins. And that's all learning from a graph. And then moving on to the next component, which is edge. At edge level, we have a link prediction task, as an example. In a social network, we can be predicting whether or not John and Amy are friends. Twitter launched this feature to recommend people to follow on their app in 2010, and that's powered by their recommendation service built on top of their social network graph. And nodes not only can be the same type, a person, or it can be mixed types. For example, Amazon creates a graph that encodes their items and their users by creating this massive graph encoding the interactions between items and users to provide an item or product recommendations for their users. Moving a level up, we have a collection of nodes and edges that forms a subgraph. We have subgraph level task, which is community detection. And moving a level up, we have the top level graph level. And there we can also learn something. A task can be drug discovery, for example. What's next? These are some fundamental elements of graphs and some common application of graphs. For a long time, we can apply traditional machine learning on these graphs based on the structure of the graph itself. Some of these structural learning can be hand-curated features based on these graph structures. What are they? Here, I'm not going to explain all of them, just an example. For a node feature can be how many neighboring nodes a node has. That can be a feature to represent a node. And on the edge level, you can count how many edges are between two nodes. That can be an edge level feature. And of course, there are more complex methods to extract information from graph level. You may also hear very often when it comes to graph learning, random walk, which is a very common algorithm to learn node representations in graphs as well. Okay, let's move on to what's being used a lot now with the big data. You might ask, okay, we have a social network, we have our users, we have all this information associated to this user. Given the traditional machine learning method, how do we use those information? That's when we move on from the traditional method to graph neural networks. Naturally, we have graph. In graph neural networks, we use graphs to encode data. And then we have our neural network, which can take on any form of architecture. Combine these two together, we have the graph neural network. It's that simple. And if we zoom in, how do we actually learn from these relationships? between the nodes and the features. Let's take a look at this simple example. We have a simple graph and focus on our target node A. What's happening when we're learning from these nodes and these edges? There are generally two steps. First, we're learning a message from the neighboring nodes of target node A. This message can be any form of function. And then we aggregate this message to form a representation for our target node A. These two steps combined usually forms a graph layer. And depending on how you choose the aggregation function and how you transform the neighboring nodes, that gives you different architectures of a graph layer. And of course, if you have multiple of these layers stacked up, you have a deep graph neural network. That's it. Here I'm going to show a very simple example based on very simple data, just to give you a taste of what it could look like, what it actually does. So I have a data set from Twitch. It consists of Twitch users and the edges between these users. These edges are mutual connections, mutual following relationships between these users. And of course, some features related to these users as well. And I have a model. What does it look like? It has two layers of graph stage layer, which is one type of architecture within the graph architecture. And then you stack them together. Then you pass into the layers the input features of these nodes. You have a node embedding. Then feed that into a downstream task. Here, I take an example using link prediction as a task. You're predicting how likely two nodes are going to connect to each other. Let's take a look at an actual example from the data. So we have our target Twitch user. Maybe it's too small. I'll just say it out loud. Some features representing this user. And we're looking at what are the users that are most likely to follow our target user. Then we look like what are the users that are least likely to follow our target user based on the predictions we are having from the model. And I'm highlighting a few features here. So here is the number of views from each of these users. We can easily see that there's some patterns. The people who are most likely to follow our target user have fewer number of views, which is very similar to the target user itself. Whereas the users that are least likely to follow have a large number of views. Another similar pattern we can see also on this lifetime feature. So the model is learning something. On this toy example where I basically spent a few hours testing it out, didn't do any parameter tuning or anything, it works. And what are the actual impact in industry that we are seeing? DeepMind recently published AlphaFold. And it says to have solved the protein structure prediction problem. Pinterest reported that there's 25% increase on impression for one of the products by using graph neural networks. Amazon has also reported significant increase in their performance built on their recommendation system by incorporating graphs. And what is Bumble saying? Stay tuned. There's more to come. Thank you very much.